Okay, in this video, what we're going to do is we're going to talk about how to do equilibrium problems. And the nice thing about equilibrium problems is that there's only two types of equilibrium problems. So let's jump right into this here. If you take a look over here, you can see that there's problems where we're asked to find the value of our equilibrium constant, or they give us the equilibrium constant and they ask us to find the equilibrium concentrations or pressures in a problem. And that's kind of nice because regardless of how they dress it up, I've heard the expression you often have, you can put lipstick on a pig, it's still a pig. If you can put whatever variables, you can ask questions, you give percentages, no matter what, an equilibrium problem is still an equilibrium problem, and there'll always be only one of two ways of attacking a problem. Either they're going to ask you to solve for the k, in which case they're going to have to give you all of the other variables, or they're going to ask you to solve for concentrations or pressures given the k. So how do we do that? Well, the primary way we do that is with something called an ICE table or a RICE table. I'll explain what that acronym means in just a second. And once you figure this out, you're going to roll through this stuff. By the way, when we say initial concentrations, and in case you were having trouble seeing the acronym here, it's RICE. That stands for a balanced reaction. The initial concentration, I want to point out something here to you. See how there's a little zero right there? We call that naught. So whenever you have an initial concentration, outside of the square brackets for your concentration, which by the way indicates molarity, we put a little zero symbol. That means that's our initial concentration. If it's an equilibrium or a final concentration, we don't have that zero in here. Our change in the concentration is going to be either plus or minus x, and we're going to deal with that in a second. And then we have to solve for equilibrium concentration. Now, again, until we do a problem that's going to sound a little bit ethereal and not make a whole bunch of sense, but one of the things you have to remember is that there's only two things you can have in ICE table. One is concentration, and concentration must be in molarity. The second thing you can have is you can have pressure, and that must be done in atmospheres or unit of pressure. And side by side, if you're dealing with concentrations, you're going to deal with a Kc. If you're dealing with pressure, you're going to deal with a Kp. And remember in our last table or last video, we gave you the ability to convert back and forth between them. The other thing, and I just said this a second ago, is that the only two types of problems you're going to have ever is if they give you a Kc or a Kp, then they'll ask you to find x in this ICE table. If you're asked to solve for the Kc or Kp, then they will have to give you all of the problems or a way to figure them out in order to solve for the actual problem. Now, this right here, this table, I'm going to referring back to it over and over again as we do. I'm putting a little star here. It'd be worth like printing this out separately so you can follow the steps as we're going along, because I'm going to be using them as we solve problems. So let's just jump right in and see how we use problems like this, or how we use how we solve problems. Now, before I go any farther, one of the things that's kind of weird is that we look at problems and we're like, well, how in the world can the k value be the same if I start with a whole bunch of different values? And I want to point this out in these three experiment runs with this one single equation. So if you note here, we have N2 and H2, and if we set up our problem here, and I always like to write my equation. So this would be my reaction up top here, and I'm writing it with the cool arrows, 2NH3. These are all gases, which is actually kind of important. And I'm going to write I, C, and E here. That's initial, change, and equilibrium. Initially here, don't I have 1.00 molar N2 and 1.00 molar H2, and I have 0 of my NH3. Now, typically in a problem, we've got to figure out which direction the reaction is going to shift to get to equilibrium from our initial amounts. That's another way of saying solve for Q, as you can see here. But in this case, we have no product, so isn't the only way we can shift this direction? Which means this: we're going to lose some of the N2 and the H2 because they're going to combine with each other and form NH3, and we're going to gain NH3. But remember, the coefficients tell us how these reactions are going to react. Wouldn't it mean that we take one N2, put it together with 3 H2s, and we'll get 2 NH3s? Similarly, another way to say that is that for every one N2 I lose, I will lose 3 H2s, and I will gain 2 NH3s. Put even more straightforward manner, if we say that the amount we're losing is x, we could say this: for every x that we lose here with N2, won't we lose 3 x's for H2, and won't we gain 2 x's for NH3? And that at equilibrium, if you look at this, we're going to end up with, and they give us the equilibrium concentrations, I'm just going to write them in here, 0.921 0.763 and 0.157. And if I were to use my equilibrium expression, I were to write it out, you can see it right here. If I were to plug those values in, my equilibrium values in, 0.157 squared, and then on the bottom, if I were to write my N2, which again, we've already put the numbers in, you can see how they've already been set up, although it's covered a little bit. It's kind of odd. On the bottom, we'd have 0.921 times 0.763, all raised to the third power. And if you do the math on that, you get 6.02 times 10 to the negative 2. And this is what's really cool about this, is that no matter what initial concentrations we start with, I can literally give you 1,000,000 initial concentrations. Every single time, the reaction will shift so that the ratios that you are given will give you the exact same equilibrium constant in every run through. Now, this is a big deal here. If you take a look at these numbers here, and these numbers here, and these numbers here are nowhere near each other. But they don't have to be, as long as when they plug them into this equilibrium expression, they give us this K. Now, they may not be exactly the same, because sometimes when we round differently in problems, but, and one of the things that's really a big deal is that one thing that can change our equilibrium constant is if we mess with the temperature, but we're not going to do that right now. But be aware, no matter what you start with, and this is what's kind of cool, at any given temperature, the K for that reaction will always stay the same. So no matter what you start with, the equilibrium values will always even each other out to get to the value that you need to get to. Again, our reactions are very stringent. They follow the K rules intently. Okay, so the best way to work out all the kinks in how we solve these problems is actually do a problem. So in this particular problem right here, they're asking us to solve for the equilibrium constant. What does that mean? That means that they must give us a way to have all of our equilibrium values, equilibrium concentrations, so that we can solve for our K. Before we do anything though, and this is incredibly important, you need to balance your equation, and this is not a balanced equation. So let's balance this guy off. Let's do a different color just for funsies here. We have 2 O's here and 2 O's here, and here we have 3 O's. I'm going to put a 2 in front of here and go, that gives us 6 right here, and then I'm probably going to put maybe a 2 over here in front of this. So 2, 1, 2, and that's going to give us a balanced equation. You can verify this on your own. Now, I also like to do this almost immediately whenever I start a problem. I like writing the K expression over to the side or at the very top of my problem, because I want to know what I'm going to be plugging in. And again, it's the products over the reactants raised to their exponents. So I'm going to go SO3. In this case, it's raised to the 2, and it's all going to be over SO2 squared times O2 squared. So let's go back, get down, and I guess I should have flipped these around in the problem, but I'm going to write our reaction. I'm going to do a Rice table here. It's going to be 2SO2 plus O2 goes to 2SO3. Now I want to point out something to you here. These are all gases, yeah? So they could have just as easily, instead of giving us concentrations, which they did, they could have given us pressures in atmospheres, and they could have asked us to solve for Kp. They just happened to use, and this is one of the cool things about this, and can sometimes be confusing. Just because there's gases here does not mean that we can't do the problem in concentration. Conversely, if we have atmospheres, we must be using pressure. So let's do our ice table, I, C, E right here, and let's write down all the initial values they give us. They give us 0.500 of this, they give us 0 of this, and they give us 0.350 of this. Now, you could plug values into our Q, and if we plug our values in here, it would be 0.350 squared all over 0.500 squared, and 0. And I put squared here. It's not being squared. That was a mistake. 0 raised to the 1. That's problematic because that's undefined, right? But a better way to do it is, if you take a look at the problem here, do you see how they gave us a final equilibrium value and final concentration, our equilibrium concentrations, of 0.590? And if we compare our initial to our final of SO2, do you see how it's gone up? Which means that the reaction must shift to the left. So I don't know why I did a dipole arrow there, but it must shift to the left. What that means essentially is that we're going to lose stuff from the SO3 side and we're going to gain stuff on the reactant side. Another way of looking at it is we have a 0 over here. Can you subtract something from a 0? No, but you can add something to it. So what is our change? And this is really, really important yet again. And I'm going to do the same process here, although there's other ways you could solve this. So remember, what we're looking for is we're looking for this right here. We're looking for all our equilibrium values that we can plug back up here into our equilibrium expression and solve for our K. So what we can do is just go, all right, how much are we gaining or losing into the side? Since we know we're shifting over to the left, we can say on this side we're gaining x's, and on this right side, or the product side, we're losing x's. Look at the coefficient. Here we're going to gain 2x. Here we're going to gain x. And over here, we're going to lose 2x. Yeah? And when we set that up, what does that end up with? Well, that gives us 0.590. Here we have x, and here we have 0.350 minus 2x. Now the question is, how do we solve for our x? Well, don't we know that, if we take a look here, between 0.590 subtracting 0.500, doesn't that give us our 2x value, right? So if we do the math here, wouldn't that be 0.09 equals 2x? And if we divide it one more time, wouldn't it be 0.045 equals x? So if I wanted to, right here, couldn't I just plug the values back in here and go, well, this x, isn't it going to be equal to 0.045? And if I took this 0.3250 minus 2x, wouldn't that then be equal to 0.260? And if we have these values, these are the three values, this, and this, that we can plug back into our K expression. So I'm going to put my K down here just so you can see that this K right here, we're just plugging the numbers in. And it's going to be 0.260 all squared all over our SO2, which is 0.590, and that's squared. And then we're going to times that by 0.045. And when you do all the math on that, you're going to end up with a K expression of 4.36, as you probably already did in your head. Now, there are no units on this K, which may frighten some of us, but just be aware that that is how this sometimes works. Now, let's take a look at this, and this is a little bit more set up for you. And I'm not going to set up the entire problem, but I'm going to set you up with the basics and then allow you to do this. In this particular problem, I want to focus on this again. What are they asking us to solve for? They're asking us to solve for the KC. If they're asking us to solve for the KC, mustn't they give us all of these equilibrium values? Now, there's more spaces in here in this table because it's a generic table, but I'm going to write in the values for what the equation is. Now, they're not gentle in this case. They don't give us the actual equation, but if I have hydrogen gas and iodine vapor, wouldn't that be H2 and I2? H2 plus I2, and it forms what? Well, the only thing that's going to really form, wouldn't it be HI, HI? And if we balance it off, wouldn't we have to put a 2 in front of this to make this work? Yeah? And then initially, don't they give us 0.085 moles of these two gases, right? 0.085 molar of this and 0.085 molar of this. This moles per liter, by the way, it is equal to the concentration in molarity. Now, here's the thing. We must, and we have 0 of this, because if they take reading this, it said that both of these gases, the hydrogen gas and the iodine vapor, are placed in a flask and heated to 700. And they tell us the initial concentration is this. Now, they say this. At equilibrium, it's found that 76.75% of the iodine is consumed. Now, if I were doing an X problem here, wouldn't I go, well, which direction is the only direction I can shift in this problem? Well, the only direction I can shift is this way, because I have none of the I2, of the HI over there, right? So that means that I'm going to lose from this side and gain on this side. Now, if you take a look at the coefficients, wouldn't we lose X here, and gain 2X here? Now, the key thing would be, if we can figure out what our X value is, couldn't we then solve for what our equilibrium values are? So how can we do that? How can we do that? How can we do that? Well, here's the thing. Don't they tell us that we have 0.085 molar I2 to begin with? and they say at equilibrium, 76.5% of this is consumed. Wouldn't that be the same thing as saying how much is left, or our X is equal to 76.5% of this? So how would you figure that out? Let me just give you a hint on this. 0.085 times, if you ever have a percentage and you want to figure out what percent it is number-wise, you make it in a decimal. Couldn't we just go times 0.765? And that would give us our value of how much we lost, which would in turn be our X. I want you to solve this on your own, and we'll deal with it in class. You guys have a blessed day.